Okay, so today we're doing chapter 8, a bunch of energy stuff. I talked about this a little bit before, potential energy with the spring stuff. So you have gravitational potential energy, the potential to do something. So we're going to go over this. It's a lot of repetitive stuff in this chapter, but it's a very important concept that you need to get down. Potential energy is usually defined as this capital U, and it has a couple of examples here. Earth and bungee jumper. So the bungee jumper starts out here. It has so much potential energy. As it jumps, the potential energy decreases as it goes down. And then you have the elastic potential energy of the bungee cord. This is the same as the spring potential energy that you did in the lab, the spring lab. So there's some spring constant K, right? And it has some potential energy as you compress it or pull it out farther than its normal resting place. It wants to has that restorative force where it wants to go back. So we need to account for all these kinds of energy because this makes it easy to get a total amount of energy. So as we transfer from one to the other, we can figure out where it's going and how much is being transferred. So it's also related by work. So the change in potential energy is then related by the negative work being done. So again, we have the change in gravitational potential energy. It's the negative of the work done, and then it also applies to the spring system because it always wants to go back to where it was. So you pull it out, it wants to go back. You push it in, it still wants to go back. So some of the important parts here are the system. So the system has basically usually a particle in it, or it can have more than one particle if it's a multi-particle system. And then you have whatever the environment is, whatever it's contained in. So if it's in like a bubble and it's a little, some kind of particle dot inside it, then that's the system, right? When the configuration changes, the force does work W1, changing kinetic energy to another form. So if you have this closed system, that's all we're looking at. So if I take some kind of bubble, I stick a particle in it, and I start moving it all around, the energy is only in the system. It doesn't matter that it's on Earth and there's all these other things happening all around it. We're not looking at that. It's just the system's the only thing we're looking at. So the reverse, if the configuration changes reversed, right? The force reverses, then the energy transfer is doing work W2. So it's just differentiating between the first work and the second work, realizing that they are different. Again, the kinetic energy must either become the potential energy or not change. These have to be conserved. So in this system, everything's conserved. Basically, it's telling you that if you have so much kinetic energy and you have so much potential energy, as one changes, the other must change exactly proportionally, right? So as kinetic energy goes down, potential energy comes up. They always must be conserved. There always must be the same amount. So you can't have kinetic energy just go up because then the total amount of both has increased, right? Or the total overall has increased. So they have to change proportionally. Conservative forces, again, so that's basically me explaining the up and down. The W1 must equal the minus of W2. So as one goes up, the other goes down. This one's negative in this case. This one's becoming more positive. This one then comes down, becomes negative. This one must become more positive. Again, they're proportional, so they go up and down. Again, gravitational and spring force are really easy examples. So non-conservative forces. So we have non-conservative forces. You have the frictional force, and then a drag force, like we talked about earlier, within like wind, a car moving through wind or wind tunnel, submarine moving through water. Those are drag forces. It's just a frictional force that's being applied to a whole object as opposed to just one side. So, and then one of the other things is, again, energy is conserved, meaning we can account for it, but it's lost from the system. So if you have the system is just a block moving on a plane, then as you push the block, the frictional force is working against it, right? It's going the opposite way. And then you're losing energy to the dissipation of heat between the plane and the block. So as this goes off, you're losing it. It has 10 whatever joules of energy. As you push it, it's going like 9, 8, 7. Of course, if you keep pushing it, then you're burning the potential energy in your body, right? So that's like a chemical potential that you have stored through eating food and whatnot. So the thermal energy cannot be recovered back, right? So this means it's non-conservative. We've lost it. It's no longer in the system. It's dissipated outward. Then we say it's not conservative. The frictional force for this is pretty much, or drag force, which is kind of the same thing, are the only non-conservative forces we're going to be really dealing with. There are certainly others, but we're not going to deal with them right now. Okay, so again, this is more along the lines of a bunch of stuff I just said, but in specific terms, the net work done by a conservative force on a particle moving around any closed path is 0. So what they're saying is that as long as it's a closed path, that it's always changing. Nothing's let go. So this is a conservative thing, right? So we're not losing any of it. It's just being changed from one form to another, but it's never disappearing. It doesn't get bigger, doesn't get smaller. The work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle, right? So again, this doesn't really matter if you're dropping an object, right, and then you zigzag it back up to get back up. It still has the same gravitational potential at the start and the same kinetic energy as it falls. Of course, when it stops, now you've lost kinetic energy and you've lost gravitational potential. But then as you pick it back up, again, it's still the same gravitational potential energy that it started with the first time. So the path doesn't necessarily, or doesn't matter in this. So some of the examples are given here is like a basketball. And we look specifically at the formula here. We see that we have an initial height and a final height. So we're looking at it between these 2 points. So the initial height is up here, and then they're looking at the final height being down here, this difference. So the difference of the path it's taking is between these 2 heights. So when it falls from the initial height down to the subtraction of the final height, that's the work being done on the system, right? So it doesn't matter if this thing just zigzags somehow magically. We implemented magic on it. Now it's zigzagging all over the place. The power of magnets or some nonsense. It doesn't matter. The potential energy has now been spent as it goes down. And then if we raise it back up, the gravitational potential energy is then the same back at the beginning. It's giving this path that's going up and then down, which I think is slightly misleading, because you have to put some kind of energy into the system to make it go up in the first place. But you're just supposed to ignore that fact and look at the fact that it was started at this point and it ended at this point, so it's the same as the first situation. Again, just hammering home the same point. We have a roller coaster. It starts here, it ends here, right? So it doesn't matter this extravagant path. It's done through loops and twists and turns, and it's ending up the same place it started. So it's going to have the same gravitational potential energy that it started with. So H naught minus HF final, like the H initial versus the H final, equals the same thing. So this is 0. So the work being done is 0, right? Okay, so more of the same. Again, now we have a cheese block going down this path. This is probably easier to picture if it's like a bead on a wire, because as this cheese block moves forward, it has to adhere to the path that it's on. And I think it's really odd to imagine a cheese block just sliding down this kind of elaborate path. So if you just use the bead right here as sliding down through the path, maybe that's easier. But basically what we're saying is the same deal. So the cheese starts here, it ends up here, right? As long as we're not considering friction or any other non-conservative force, it doesn't matter. The path can just be a straight line, or as we do everything in physics, right, we break it down to one dimensions, x and y axis. So it just goes this way, then it goes this way. Already looking at this, you should know gravity does not act in the x direction. So no work is being done here. This is more of the same. This is just, again, slippery cheese. There's no friction. So we choose the easy path. Obviously, we don't want to do more work. We're lazy physicists, so we ignore the path and we just do it this way. If you had to use the curvy path, obviously it would be a lot more difficult. You should get the same answer if you're doing it correctly, but it's a lot more work. Okay, so if we look at this again, the work done in the horizontal path is cos 90, therefore it's 0. Right, so the work being done in the horizontal is 0. The work done towards the gravity portion is then an answer, right? We have a numerical answer depending on what the inputs are of MGD. So you might ask yourself, okay, so this thing moved in the x direction, right? Why was there no work done in this direction? Because the potential energy that's acting on it is the gravitational. There was no push at the beginning in the horizontal. So that force times distance, remember, does not act in the x. The only thing that's acting on it is pulling the cheese down. Now it has to adhere to the curved path, so the initial energy it has from the gravitational portion is what's supplying the energy as it moves through this up and down path. So don't be confused just because it moved in the x that somehow it's done work in the x. The only energy that's being applied to it is in the downward y direction. So, and then it's just a example problem in the book, so you can go through the numbers if you want. So some of the other things we're looking at here is work still defined as the force times the distance. If we're doing the integral portion of this, because it's more complicated, the force times the infinitesimally small x portion of this, and the x final minus the x initial, which is just the distance. So that's our standard definition of what's going on here. So we have to remember we can start interchanging terms here. So we have a potential energy. So we have the change in potential energy is the same thing as the force times the distance, right? So we're using this to calculate the gravitational potential. Again, this says relative to a reference configuration with a reference point. So this has to do with the system versus the body again. And then this is just a simple force times the distance, right? MGY, same as MGD. If you're doing gravitational portion of it, then we're just using y instead of d. And then again, these points down here are kind of like really key, concise points. The gravitational potential energy associated with a particle, the Earth system, depends on only the vertical position y or the height of the particle relative to the reference position. They're saying reference position because if you have the Earth and you have some particle, if you say it hits the ground, then it hits the ground. If you have a table on the Earth, a massive table that's as big as the Earth apparently, then that's your reference position, right? Because that's going to hit the table, not the Earth. So that's what they're just talking about. Wherever you set your y to, whatever the particular situation is. And it's not dependent on the horizontal. Okay, we got some mass here. So again, this portion here is just your force, right? So we got your force times your distance again. So it's the same thing as we just did. This was your force portion in the x direction. Same thing, we're just substituting in that force for now what is Hooke's law, right? K times x or minus k times x. And now we've substituted the work for the change in the potential. So this is still the same as your work equals your integral of force times dx, right? It's the same thing. We're just substituting in these pieces. Now for this portion, we are getting out this this familiar equation from the spring lab that you've done. It's the 1/2 kx squared. So when we look at the change in potential, if you subtract the final energy with the initial, that gives us the change in potential energy. And then again, you have this reference point that you set where the x initial equals 0 for a relaxed spring. So relaxed spring meaning it sits, you're not touching it, you're not doing anything to it, it's just the initial position where it sits. So if you pull it, that's no longer the initial position, that's a final position, right? And you want the difference between the two. Okay, so mechanical energy of a system. This is the total kinetic plus the potential, but it's just of moving objects. So we're not getting things like chemical potential or thermal potential. Those aren't included in the mechanical. That's a different form of energy. So the mechanical is basically just things moving. We're pushing things around with forces, etc. So we can sum up the potential, and this is just basically saying that these things are interchangeable again. So you have the mechanical energy is equal to the kinetic plus the potential. So again, that conservative system, things are moving up and down. The total of these two, if one's kinetic and one's potential, is just the mechanical. So the change in the kinetic is then the work done. So get rid of that. The change of the potential is then just the negative of the work. So the change in the kinetic must equal the negative change in the potential, right? Because again, these things are conservative. Therefore, change in kinetic plus change in potential must equal 0. Because again, that's all there is. There's potential, there's kinetic, and they're just interchangeable, but it must equal 0 if it's conservative. So again, you have you can have starting pieces and finishing pieces, right? You can have some initial kinetic, some final kinetic, same thing, initial potential, final potential. And this gets more into the second ballistic pendulum lab that you would have done. I don't know how many of you are still going to labs. No one's going to my labs anymore. But basically where the ball shoots out, and instead of going over a path and dropping downward, now it hits the basket, goes inside the basket, and then the basket climbs upward because of the arcing piece that's here. So basically what's happening is the ball's coming into the basket. It's pure kinetic energy, and you started off with spring energy. So I'll just do the whole thing, I guess. So you take the spring, you push it in. You've used your chemical energy in the body technically to do work on that system and put energy into the system. Now the system has a total amount of energy in that spring. That's the total amount in there. We're not considering anything else. So the ball flies out. Now that potential spring potential energy has been converted to kinetic energy of the ball flying. It goes inside the basket. Now you've combined two different masses. You have the mass of the basket and the mass of the ball. Now from this point on, you have some kinetic, and now it's being converted into gravitational potential, because no longer is it sitting on the x-axis, the horizontal, it's moving upward, right? So with each degree it changes, it's moving higher and higher. As you probably would guess, it's getting higher, it's going to slow down, right? So you are directly converting the gravitational or the kinetic energy into gravitational potential. So 100% kinetic here, hits the basket, starts to move up. Now it's like 80% kinetic, 20% gravitational potential, etc. It keeps changing. It's 50-50 until you get to the top, and it stops. Here it's 100% gravitational potential energy, 0% kinetic. But it should, the gravitational potential here should equal exactly what the spring potential was at the beginning. You're going to find out this doesn't happen because it's real life and there's other forces at play, which one of the questions is going to directly ask you about. The piece of advice I would give you for that, and a lot of the lab instructors aren't even smart enough to know the real answer to this, but the real answer is not that the lost energy is in heat and sound. The amount of heat and sound generated from that ball and basket going upward is very, very small. You're going to get a very high percentage of energy lost, and it's not from that rising. If you ever want to know what it is, you can ask me later on, or if you're Instructor says no, it's heat and energy. They're wrong. You can also ask me about that. Okay, so moving on from the slide, giving away all the secrets of the labs. So rearranging, again, we just did this same thing, sum of the kinetic and the potential, basically sum of the initial, sum of the final. So again, we're talking about an isolated system, so it's conservative forces here. It must change between kinetic and potential, but again, their sum is this mechanical energy. That is the sum total of potential and kinetic interchanging. So yeah, we have this piece down here, kind of already did this. It's going to equal 0 because it's conservative. Again, this is the same thing. We can relate the kinetic and the potential at any one instant, meaning boom, it's here and here. You have some kinetic, some potential, you add them up, that's the total energy of the system. Boom, system changes. Some kinetic, some potential, still the same. Are you getting this point yet? It's been literally like 20 minutes of me going over the same point. Everything's conserved. Which the fact that it is conserved allows us to solve for information that we might not otherwise be able to measure, right? So it's useful. Okay, so here is a pendulum. And I don't remember, I think I posted something about this for you guys also. The potential is essentially the same as the spring. So the pendulum sits at the bottom, at the bottom of its arc. So the gravitational potential for this system, because the system is just basically the ceiling which it hangs from, the environment here, and then the particle that's at the end of the little ball. So for here, this is the lowest point it's going to get to. So the gravitational potential at this point is 0. As you move up, gravitational potential increases. So again, kinetic energy decreases. Now we're full gravitational potential, it's going to swing back. Same thing, kinetic energy is as fast as it can possibly be at this bottom point because the gravitational is 0, goes back up, changes. So it's constantly flip-flopping between kinetic and potential. And that's all this thing is, elaborately done over and over again. So this point here is actually the same as this point here. It's just on the other side. Should be the same angle between here. Like this angle between and this angle between should be the same angle. Therefore, they have the same kinetic and the same potential because it's basically just a mirror of the system. And then they're just showing here exactly what I'm saying with these things bouncing up and down. At the very bottom, it's 100% kinetic, right? There's no gravitational potential. At the very top, did they do it at the very top? Okay, at the very top over here, it's 100% gravitational potential, like I said. So yeah, hopefully you got the point of that by now. So, again, conserved. Mechanical energy system is conserved. We can relate the sums of it any instant. Blah, blah, blah. So more of the same stuff. Again, if you find a place where the potential is 0, then the kinetic must be a max. Again, because I've already gone all over this. But that's just a piece of information if you're trying to figure out something. Because you know these book problems are giving you, it's all different situations, right? So if you find out that the whatever potential energy is at max, then the kinetic energy must be at its minimum. Okay, so here's another situation. Again, just hammering home this same point. You have some bobsledder going down this elaborate back and forth path. You have an initial velocity of 0, meaning no one's pushing it, just gravity is pushing this thing down. Since it's conserved, it's the exact same energy every time. That means there's no friction. This is a frictionless system, right? So at each point, no matter where you take it, the total amount of energy is going to be this 600,000 joules. So at the bottom, you've lost all the gravitational potential, right? And it's been all converted to kinetic energy. So same stuff. Again, just killing this point over and over again. Doesn't matter the path. You can figure out the height, you figure out the potential, therefore you know the kinetic energy at the end, therefore you can figure out the velocity if you want the speed. And then again, this just goes over it. So again, you kind of have initial situation versus final situation. So they're using bottom and top. So this is the initial over here. This over here is final. And then you have kinetic energy. This is kinetic energy. This is potential. Or U, I guess we'll use. So you use U for potential, K for kinetic. This is the kinetic portion, so this is the initial kinetic energy. If the little girl starts at 0 and is only using gravity to pull her down, this whole part gets zeroed out, right? When she gets to the bottom, then there's no more gravitational potential because she's at the bottom of the system, which is being defined as right here. So this is 0. So this becomes a lot more simple given certain conditions. So you can solve with the information given and you get this number. Again, it's another example problem in the book. Okay, so reading of an energy curve. This is kind of interesting, probably not for the reasons that you think I would think it's interesting. But we're back to the same thing. Change in potential equals the negative of work. Okay, battery in this camera is supposed to last 3 hours. Apparently it can't handle the topic of physics and lasts nowhere near that. Where was I? Okay, so again, you have the change in potential must equal the negative work done. So again, we have this force times distance. In this case, it's negative. And then so basically we're saying the change of x here, if you rewrite this, the change of x, the potential of x, if I say that correctly, must equal negative force times the change in x. Oops. So again, you take the potential and we move this over here, right? So then you have f of x equals the change in the potential over the change in x. So if we use this in differential terms, because we want the infinitesimally small version, so it's 100% accurate, you have the change in potential, or du over dx. So this gives us information that we can manipulate later using calculus, so it makes it easier for more complicated things. So you can find the force from plot of the potential energy. Take the derivative of the slope. So again, you have total mechanical energy, this combination of these two, and we can manipulate these with algebra back and forth depending on which information we're given. Okay, so yeah, again, exactly what I just said. The only interesting thing here is that in the plot, when k equals 0, that is a turning point. So the kinetic energy is then 0. So an example of this would be like taking a ball and throwing it straight up. So you take the ball, you throw it straight up, kinetic energy is at a max at the bottom because you initially gave it some push. And then it decreases until it hits 0. This is then a turning point, and then it changes direction and comes back down. So that's what they're talking about when they say that it's a turning point. Kinetic energy is 0 and then starts increasing as it goes the other way. Apparently the cat wants to say hello. So you have the equilibrium points. The slope of the potential is then 0. This will be easier when you look at the graphical version here in a second, I think. A particle is then in neutral equilibrium, and neutral equilibrium is what they're talking about when it's like a ball on a table, right? So a ball on a table, it doesn't matter which way you push it, it's going to stay in that same equilibrium point. And that's what they're saying here. Okay, so if it's displaced to one side slightly, it would remain in its new position, meaning it's on like a tabletop. If it was on like a curve like this and you have a ball, you push it one way, it's going to roll, right? That's what they're differentiating between those two differences. Jeez, very hairy. Go back to your chair. Okay, so unstable equilibrium is what I just explained. That's when you're on like basically a hilltop and the ball is going to roll either way. And then stable equilibrium is basically the opposite when it's in like a valley. So it doesn't matter if you push it either way, it's going to go back to that exact same spot. So here's the graphical version. So this is a plot of potential versus the X. And again, what we were talking about here before was if you have a particle at a certain position, this is technically unstable, right? So if you pushed it to the left, it would remain in the same place. If you pushed it to the right, it would start sliding down this path. So that's unstable. This is another point right here. So if you had some particle at this little hilltop, you pushed it either way, it's unstable. It's going to fall into one of these wells. Something that's stable would be right here at the bottom, right? So when it's stable, it means it's going to always go back to this point. It's okay if you push it and it moves somewhere. It's just the fact that it's going to go right back to where it was. Okay, and then a neutral equilibrium would be like up here, right? At least to a certain distance. Obviously, if you push it way over here, it's going to go down. But if you remain within whatever distance, it doesn't matter. It's just you're going to move it, it's going to stop, it's just sit there. Neutral equilibrium. Okay, so what they're doing then is they're making a force versus X plot, and it's based off this guy. So if we look at these points exactly, we look at X1 and we look at X1, and we kind of draw this up here. This is happening, somewhere around here, and this X1 is happening somewhere around here. So you have some positive force acting on this thing, meaning this thing is, we'll say it's just a ball sliding down this ramp. It's sliding down the plot. So right here, it's experiencing some force, and that force is increasing as it goes up. Now, if it is a ball falling down here and it's gravitational force, it's working the opposite way. This whole plot has to flip the other direction. So then as it hits the bottom, it's going back up. We look at X2 right here, and we see that the potential energy is 0. Therefore, over here, it's basically 0, but it's a turning point, right? Because the kinetic energy is basically equaling 0. And then it changes. It's a turning point, so it's going from positive force to a negative force. And then we look at this point between X2 and X3, and we're saying this is a mild force. It's in the opposite direction. So we can see that this is not as high. Between X2 and X3 is here. It's something, 1.8 or so, as opposed to X1, which was maybe 4.5. So it's a difference in the magnitude of the forces, and then you can see as it changes here. Okay, so we have the functions here that we're talking about. We can figure out the strongest force acting on the particle because of this. We can find out the weaker forces acting on this. So again, it's just information. So here you have what is the total mechanical energy of the system. So again, this was the total interchangeable pieces of this, meaning that this is the max. This is the total everything can equal. So basically nothing can go above this. This is where it gets kind of interesting. This becomes an introduction to quantum mechanics, which I'm assuming absolutely none of you are going to do anything with, but we use the same ideas with this. So if you have, like, say, an electron down here, it's in a well. No matter which way you push the electron, meaning you add a little bit of energy to the system, like if you have a nucleus and you have an electron here orbiting around it, if you push it out a little bit, it wants to go right back to it, right? You push it a little bit towards the nucleus, it pops back out. It's like a spring, basically. So same thing here. You push it one way or the other, it's not going to go anywhere. In order to get it to a new position, to get it to like a second level where it wants to orbit, you have to add enough energy to overcome this hump, right? You got to push it up and over, and then it's going to sit in this guy. So that's like the second state. That'd be like the second ring that it's orbiting, like n equals 2, right? So kind of interesting. We use the same principles for more advanced stuff like quantum mechanics. Obviously, it gets more complicated. The math gets more complicated, all that stuff. But just a little, give you an idea of how some of this stuff works. But again, if the total mechanical energy is then reduced to this point, then it can't get out, right? Because no matter how much energy you give it 100% of the energy, it can only get to this point. That's the total energy. So it can't get out of that little well. Okay, so they're also talking about the differences here. If you figure out where your potential is at some point, say here, you know the total. So you can subtract these points. That is terrible. You can just use this line they drew right here, and you can figure out the kinetic energy. So from the plot, you have the potential, you have the total, therefore you can figure out the kinetic. That was the little equation they were rearranging at the beginning. So down here you have the total mechanical energy, and then you have the potential energy at a given point, and therefore we can find out the kinetic, is what it's saying. So same stuff. They're saying where the turning points are. So this is at a turning point now, which is a little bit different. What I originally said when we didn't have the total mechanical energy. Now we have the total mechanical energy. So when it hits this point, then this is the turning point. This part is then the fastest because we know the kinetic energy must be the greatest because now we know the total mechanical energy. And the potential energy is also at a minimum, so the kinetic must be at a maximum. And then same thing, you can subtract them here and figure out the kinetic. This goes along the lines of what I was saying earlier, where it becomes trapped. So this is actually, if you can continued this upwards, for instance, this is what the energy levels of like an electron look like. And you get these things progressively get closer and closer until they're like infinitesimally close. But basically an electron cannot get out. It's stuck in that orbit. So it's just like the classic Bohr atom, and I can't draw circles on this pad worth a damn. But if this is n equals 1, then this would be like n equals 2, and then there would be like an n equals 3 up here, etc. So same type of deal. This is a spring, right? And as you push it either way, it won't go out unless you break the spring. So you need enough force added or energy to the system that this is going to break out of this well and get to the next well. So again, I know you're not doing quantum mechanics or anything, so I don't know how. I just thought maybe it was interesting if you wanted to know. But all these things still apply to it. So your pendulums, your springs, etc. Okay, this goes back more towards the systems. So the system we're saying here is the Earth, as in the ground down here, and then this bowling ball, which is right here. So that's our particle. So you have a particle in some environment, and together it's the system. You have the same stuff reinforced that we've already done. It's frictionless, therefore everything must be conserved. So now we're going to talk about the external forces. So here you have, like I said, your total kinetic and your total potential is here in the mechanical, and then you have an outside energy which still needs to be accounted for if it's there, because everything has to be conserved. Like the energy just can't magically disappear. Energy can neither be created nor destroyed, per the laws of thermodynamics. So the thermal is here. It's just no longer a part of the system, so it's dissipated into something else in the system. So yeah, we're saying we're pushing this. I used this example at the very beginning. You're pushing a block on a plane. There's some frictional force acting against it. Therefore, it has to dissipate the energy it's losing in the form of heat. So same thing, we look at where the thermal energy is being applied and dissipated from. This is more of the same stuff we already did. So here you have Newton's second law, F equals ma, except we're doing the summation of forces in the x direction. So you have the applied force, you pushing, and that's being subtracted from the frictional force because that's opposing it, still equals ma. Again, the same equations we went through in the last lecture using the kinematic equation. You can solve for the acceleration and then plug in our other values the same way we got before using the equation 828. You can get the kinetic energy portion in here. And then this becomes the difference in the initial kinetic energy. Therefore, it turns into this changing kinetic down here. And then from here, we're saying that the changing kinetic must also equal the change in total mechanical energy. So that gives us, again, a piece of information, and I'm covered in cat hair now. And therefore, this other portion that we have accounts for the total work done. Remember, this is the total work, it's force times distance. So this is then the total thermal energy, because this is the frictional force multiplied by whatever distance it went. That's why I was saying before that the path doesn't matter if it's conservative. But now if it's non-conservative and you have a frictional force and you have this path that goes like this, now you're dissipating energy throughout that path. So that path becomes very important where it's going. Hopefully that makes sense. So if there's no frictional force and it's just sliding along, it doesn't matter if you go from here to here. But if it's dissipating energy the entire time, you need to know the length of the path it's going. So it becomes a different problem. Okay, so yeah, we have the thermal energy. What are you doing? So you have the total mechanical, total thermal. We did that. Okay. So again, same principle that things are being conserved. So if you have a total system, it's enclosed, we have so much energy inside, we have exactly 100 joules, it can't change. It can only change forms between potential and kinetic. So if you add energy to the system, that's directly accounted for. If you add 20 joules of energy to the system, it must be now a total of 120. So that's what it's saying down here. So if you have, you add, say, 20 joules of thermal energy to the system, it must be added to the total change in energy. So that's the work done. Again, everything is accounted for, always. Nothing magically disappears. Total energy of the isolated system cannot change. Again, if it has no path to get out, it can't change. It must equal 0. This is, again, everything's being accounted for. It must equal 0. Again, looking at the exact moments in time, same deal, has to be conserved. This becomes kind of an interesting example. So we say the skater is pushing herself away from the wall, and because the friction between her and the ice is very low, in this case, I don't know if I think they're probably doing it 0, but there is technically friction between a skater and ice. It's just very low. So, but when you push away, Newton's third law, right, as you push against it, it must push against you. So the wall's technically the thing pushing against you. But we're looking at this, she is essentially, because we're looking at energy and not the forces per se, the internal chemical energy that we're talking about that she used when she ate food has then allowed her to push. And then when she pushed, the wall pushes against her, so she goes flying backwards. That is the initial push, that's the initial force, so that's the initial energy that was put into the system. So now that is the total energy of the system. And we're saying her kinetic energy is changed from the wall, but the wall didn't provide the energy. She provided the energy. So again, you don't want to mix up the forces and the energy working here. So one last thing, the power. So again, a power is like an energy usage over time. Again, if you don't remember this, just remember that the power that's in your house is run by like kilowatt hours. So when you get your bill, it's in some measure of kilowatt hours. So you got 1,000 kilowatt hours. That's what you're billed by. You're billed how much energy used over a portion of time. So that's what the power is in the same thing that we're doing. Power is going to be registered different for different examples, but you have some change in energy over some change in time. So again, the instantaneous power is the infinitesimally small change in energy versus the infinitesimally small change in time, right? So this gives us our differential portion. And then just summation. So again, like always, if you have questions, email me. This is going to relate to some of the stuff you've done or will do with the labs. So let me know if you have questions.